Hello, and in this video we're going to be looking at the kinetic energy of particles, particularly particles approaching the speed of light, travelling at relativistic speeds. Our Newtonian definition of kinetic energy is given by a half mv squared, this equation here. Now if we were to plot a graph of that with velocity down the bottom and kinetic energy up the side, we'd get a parabola, a smooth curve, and this graph would continue to travel past our point of 3 times 10 to the 8 meters per second, or c, the speed of light. So this equation produces values of kinetic energy even when the particle is supposedly travelling faster than the speed of light, which obviously isn't the case. So we need to have a bit of a think about how we work out kinetic energy. So let's have a think about what the total energy a particle can have is. Well, it's got some rest mass energy. As we know from Einstein, the rest mass energy of a particle is its rest mass times the speed of light squared, E equals mc squared. So the total energy of a particle is its rest mass plus the kinetic energy that the particle has. We can rearrange that to make it equal to kinetic energy, and that is the total energy of the particle minus the rest mass energy of the particle. Okay, we know what E naught is. That's E naught equals m naught c squared. So how can we define E then? Well, E in this case is again equal to mc squared, where this m is the relativistic mass of the particle. Now, how do we work out the relativistic mass? Well, we times it by gamma. And so this equation then becomes E equals gamma m naught c squared. So we can pop that into our equation for kinetic energy. So our total energy, which is gamma m naught c squared, minus our rest mass energy, which is m naught c squared. Okay, now we want to have a look at what happens at different speeds. This equation is derived from Einstein's equations for relativistic particles, but we want to make sure that it works for everyday particles as well. We want this equation to still hold true for particles travelling at low speeds. So let's have a little think about how we'd go about working that out. Well, what is gamma? Let's start with that. Gamma is 1 over the square root of 1 minus v squared over c squared. That's really important. Everyone needs to be familiar and able to handle what gamma is. And so if I just scroll down a little bit here, we can then expand this. We can include gamma in this and expand it. Now I'm going to do an evaluation of this equation using the binomial expansion, which I'm not actually going to do on this video because it's not necessary to the physics part. But if you want to have a look at some other websites and have a look at how the binomial expansion works, you'll see that the result I get is through using that method. So I'm going to expand this part here. All I'm going to do is move this m naught c squared onto this side of the equation and expand this using the binomial expansion. Okay, so we do that, and then we've got m naught c squared times 1 plus a half times v squared over c squared. That's coming from this term here. That's the one we plug into the binomial method, and then 3/8 v squared c squared, and we could go on and add a whole load more terms, and we finish that off with m naught c squared. We need to have a little think about what these terms actually turn out to be. So at low speeds, let's say our speed of particle is 10 meters per second. That's a pretty reasonable speed. It's an everyday speed. It's, well, Usain Bolt ran 100 meters in just under 10 seconds, so that's about the speed he was going. So it's an everyday sort of speed for cars, people to maybe travel at. It's also a nice round number, which makes it easy to deal with. So what happens if we put this value into this particular term? Well, the 3/8 is a constant, so let's not worry too much about that. And that's times by 10 squared over 3 times 10 to the 8 squared. Now the 3 times 10 to the 8, this is going to be a massive number, a huge number. And 10 squared, that's just 100, so we've got a small number divided by a big number. That's going to leave us with a very, very small number. And we're only going to have 3/8 of that. So in terms of this whole equation, remember we're talking about kinetic energy here. The kinetic energy isn't really going to be greatly affected, if affected at all, by this term here. So we can discount terms from this point onwards. We're not going to include them in our equation because they're just too small. It's not worth the effort of going to the trouble. Okay, so what does that leave us with then? Remember, we're looking for kinetic energy here. This is the kinetic energy of a particle, and we're now looking at particles at low speeds. If, for instance, we were travelling at a high speed, I'll use red for this one, if, say, our velocity was 2.9 times 10 to the 8 meters per second, so pretty damn close to the speed of light, we'd have 3/8 of this number here. Well, let's use 2.8 because I've written 8 by mistake. That squared, which is a pretty big number, divided by 3 times 10 to the 8 squared. So we've got a big number divided by a big number. If this was 3 times 10 to the 8, this would be 1. So it's slightly less than 1, which is going to produce a significant result. And therefore, at higher speeds, these terms increasingly become more and more important. But at low speeds, we can acknowledge that they don't greatly affect the kinetic energy. So let's go back to our low speed set of circumstances. So we've got m0 c squared, then our important terms 1 plus a half v squared over c squared, and then we've got to remember our m0 c squared on the end, that's coming from there. It's a little bit complicated still. I'm sure we can rearrange this to make it look a bit nicer. So what I'm going to do is I'm going to expand this bracket out here. So we've got m0 c squared plus a half v squared over c squared times m0 c squared, and then at the end we've got our minus m0 c squared coming from there. At the start and at the end we've got m0 c squared. The one at the end is taken away, so that one cancels with that one. Those two disappear. We don't need them anymore. So we're just left with this central term here. What else can we cancel from here? Well, we've got a divided by c squared down here and a times c squared there. So those two can cancel out as well. What does that then leave us with? Well, we're left with a half v squared m0. Remember, this is for the kinetic energy of a particle. So, rearranging that slightly, you imagine where this is going. I'm going to replace m0 with m here, just for the sake of clarity. And we're left with a half mv squared, which, if we go all the way back to the top here, is what we started with. Kinetic energy, a half mv squared. So what we can see from that is that at low speeds, Einstein's equation of relativistic kinetic energy still holds true. We know it holds true at relativistic speeds, and now we also know it holds true at slow speeds as well.